Hi, I hope you are doing well. I'm Mary Walker, and I'm presenting at UURAF for Generalized Golden Ratios, and here is my presentation. I was mentored by Dr. Iglulu Zalegi. And so to start with, the Fibonacci sequence is a sequence where you take the first number, and it's a result of adding the last two numbers. So it starts with 0 and 1. And so you see it goes from 0, 1 to 1, 2, 3, 5, 8, 13. And so you can see, like with these examples here, the fifth number is the fourth and third numbers added together. And this tends to 1.618, or the golden ratio. We're going to discuss its uses later. And so you see that it can be modeled as well with 1 plus fifth root uh, over 2. And so these graphs over here, you can see that to a certain number of instances, it clearly models out to 1.618. You might ask, what is this line here that buffers? That's just to the sixth, it goes from 2 to 1.5 to 1.6, and then it tens out. So then its uses and appearances in nature, you can see it in nautilus shells, the way it curves around the golden spiral. Roman architecture utilized the golden ratio and the golden spiral to fortify their buildings. And in photography, it's even useful to allow yourself to take in different parts of the field and note different subjects. And so most of the research was focused on randomized sequences, especially the randomized Fibonacci sequence. And so this sequence begins with parities. It begins with 0 and 1 as well, but the parities can instead be randomized. So instead of just adding, it can subtract the second number as well. And so this is a 50% chance for both ways. It can either, it's a 50% chance of adding or subtracting the second part. And because of the randomness, there's no consistent sequence for this nature. And so a lot of the differences you'll notice doing the math is that with this randomization of parities, you can get negative numbers and 0. And so because of the 0, you can't use the normal ratio to get a trend because you can't divide by 0. And so a different formula has to be used to find the growth trend. It's the absolute value of that number rooted to the nth. And this formula was found by Divakar Viswanath. And this tends to 1.13, as he found. And, it's different because this was a different instance. I ran to 5,500. But it can change, but it tends to be around this number. And so what you'll see that is that what I was testing was randomization does not have to be evenly split between adding or subtracting. You can change it to be 60-40, 70-30, whatever number you desire. And so what I would call this is a bias coin test. And so the bias going towards the additive sequence would tend to go towards the golden ratio. So you can see here with this pictures at the bottom, the addition bias 50%, it's closer to the 1.13. But then as you increase the addition bias, it's closer. You see it's an increase. It's approaching 1.6, and it'll be closer to 1.618. And so with the subtraction, 50%, same as the addition. But then when it's more subtracted, it goes closer to 1 instead, because you're losing more numbers. And so what we also studied was the Fibonacci sequence. The Fibonacci sequence is the Fibonacci sequence, but you add the third term. And so you have to start with 0, 0, 1. And so it goes 1. So you see the example here. And it tends to 1.39 or 1.839 with this, and it can use the same normal ratio because there's no zeros that can occur beyond the starting two. And it's the only real root for this cubic function modeled. And so I also modeled the tendency for it on the left here. Same behavior, spikes really high here, and then tends out. And then same thing, it starts at 1 and then models out after. This is only the 6th instance. It does not take long at all for it to go to normal. And so we wanted to see as well how the random Fibonacci would be. The random Fibonacci, I modeled up to the 1500 instance. You can see it spikes and changes because it's randomized, but it'll tend around this line in 1.2, which you can see here, it's a 1.2. Everything else is about 1.22 and everything else behind it. But that's what it tends to. And so for this one as well, you can add or subtract the second and third, so it can be these pluses and minuses. And here are the options here at the bottom. You can see add all of them, add and subtract, last one. It can be a lot of different randomizations, but they all tend to this number, which is different than you'll notice than the a little bit higher actually than the Fibonacci, which is an interesting behavior to notice. So then one of the issues I ran into was actually hardware limitations, because with these things, the Fibonacci and Fibonacci, you can go up to, I was able to run up to like the 100 thousands, and it was able to, my computer was able to handle it. But with the randomizations, I have a good computer, it couldn't exceed 5,000. It would stall out. I would use Python Spider and it wouldn't be able to work. And constants, coefficients, which I'll explain later, they multiplying in certain coefficients would that would also stop the program. It would go to, once I hit 5, it would stop working. And so with the constants and coefficients that I mentioned, the Fibonacci multiplying coefficients in, it's taking 3 numbers of my choosing, A, B, and C, and you just attach those to the 3 terms. So, A of F minus A of S, A times F sub n minus 1, and so on. And so I have an example here. You can see different behaviors modeled by it. If A and B are 1, but C is 0, you're going to get the Fibonacci sequence logically, because you are quite literally just multiplying the Fibonacci sequence once again. And so this continues infinitely, but the growth depends completely on whatever constant you multiply in, and I was not able to find a trend necessarily for whatever kind of constants could determine what. And so for the future, what I would want to find is different constants that can turn the Fibonacci sequence, in the Fibonacci constant specifically, into the golden ratio without C being 0, and having all of them be non-zero, hopefully. And there'd be investigation as well into the different biases that can turn the Fibonacci into the golden ratio, because I found that some of them could hit the 1.68, but it would get close and not necessarily work. It was an interesting behavior. And then as well, I would want better hardware, more opportunities for higher level computers to compute these high level coefficients, because as I said, with the Fibonacci, it wouldn't work above 5. And so with that, I would like to acknowledge and give special thanks to my professor, Dr. Glilu for the opportunity to do this research. It's been a lot of fun over the last few months. I am proud to be funded as well by the Lyman Briggs College Research Fund and Pathway to Research. And a special thank to my friend, Meher Dudeja, because he's helped me a lot get through my research. So I hope you enjoyed my presentation, and I hope you all learned something. Have a good night.